my dear students, so yes, we have come up with your most requested rapid revision in 20 minutes for the chemistry. So here we are going to first start with the solution chapter. So yes, we are also planning to come up with the sessions in physics and mathematics and biology as well for the rapid revision. I guess that's gonna help you to boost up your knowledge and your practice for the upcoming board examination to a next level. So yes, without further delay, let's get started for a rapid revision on the chapter solution. Yes, so first you can see these are the types of the solution that you can expect. First is solid solution, liquid solution and gaseous solution, and next you can see these are the examples of the gaseous, liquid and solid solution. So whenever you are using, let's say, gaseous solution, your solvent must be gas and solute can be in three different phase. And your common example for the gaseous solution, it can be the mixture of oxygen and other gases, camphor. For solid and gas, if you just look at then you can see camphor in nitrogen gas. For the liquid and gas, you can get chloroform and nitrogen gas, etc. For liquid solution, definitely the liquid should be the solvent and solute can be gas, liquid and solid. You can see the example related to it, it's also given. Next you can see solid solution, solid must be the solvent and the solute can be gas, liquid and solid. Please remember the examples given over here. Remember solid also can form a solution, and one example is copper dissolved in gold. Okay, let's proceed further. Here we can discuss about the concentration terms. We will discuss mass by percentage, volume by percentage, mass by volume percentage, parts per million, mole fraction, molarity and molality. So one by one, let's proceed. Whenever it comes to the mass percentage of the component, it is basically look at the formula, remember the formula, and that's gonna help you. So while just going through the section, please make sure you are taking the screenshot or you are writing down the formula. That's gonna really helpful. Okay, next you can see mass of the component in the solution divided by total mass of the solution into 100, means in the numerator and the denominator portion both is going to be same unit. So what does it mean actually? Means if a solution is described as 10% glucose solution in water, it means I am having 10 gram of glucose that is dissolved in 90 gram of water. That gives you 100 gram of solution overall. Next you can see we can discuss about mass by volume, right? Weight by volume. So what is that? That is basically mass of the component in the solution divided by total volume of the solution into 100. So for this particular case, it is extremely used for the medical purpose. Okay, so in case you are having any kind of ointment, you can check over there, the composition is written in the weight by volume percentage. So here you can see parts per million. So that is basically used for the very diluted solution, like let's say I am measuring the air pollution, the dust particle present in the air or the dissolved oxygen present in the water, those things. Okay, so that is basically number of parts of the component divided by total parts of all component in the solution into 10 power 6. Okay, one example is given. A liter of seawater that weighs almost 1030 gram, that contains 6 into 10 power minus 3 gram dissolved oxygen. So you can see it's a very small amount. Okay, this type of small concentration can be expressed like 5.8 gram per 10 power 6 like ppm of seawater. Okay, this is how. Next you can see molarity. So this is your formula, number of moles of solute divided by the denominator part. Remember, it is volume of solution itself, okay, into 1000. Okay, so number of moles we can break it by given weight divided by molecular weight into 1000 divided by volume of the solution, right? So what does it mean by 0.25 molar solution? It means 0.25 mole of that particular solute is present in 1 liter or 1 cubic decimeter of a of a solution. Okay, let's proceed. Here you can see this is molality. Molality, in the numerator part you are having moles of solute, and in the denominator part it's very important, it's going to be mass of solvent, not solution, mass of solvent. Okay, again the number of moles can be breaking down in the form of W2 by M2. So let's say if you are having 1 molar solution, it means, let's say they have taken the example of KCl, we can also take KCl. 1 molar KCl means 1 mole of KCl means 1 mole means molecular weight. That gram of KCl is present in 1 kg of water. That's it. Here you can see next topic we will discuss about the solubility. So solubility, it can be first solid in liquid, next it can be solubility of gas in liquid. Okay, so whenever it comes the matter of solubility of solid in liquids, then few factors come. First one is the nature of the substance, next is the temperature, and next one is the pressure. So first, if you just discuss about the nature of the substance, here comes the concept of like dissolves like. Let's say I am having a polar solute. Okay, so it will definitely choose to be well soluble in a polar solvent, right? Now let's say you have taken a very non-polar solute. Let's say I have taken oil. So definitely oil will not be miscible or soluble in water. It is a non-polar solute. It needs a non-polar solvent as well. So this is your like dissolve like concept. Okay, so here you can see some example is given. Sugar is soluble in water, but if you just look for the naphthalene and anthracene, it is not soluble in water, rather it is soluble in benzene because they are organic solvent. Okay, next here you can see it's all about the temperature. So for the temperature, if del H is greater than 0, means enthalpy of the mixture, then definitely the solution, for the solution it is endothermic, right? Then what happens if you increase the temperature, then your solubility will increase. But if you see your solution process, your solubility process is exothermic, then decrease your temperature, your solubility will increase. Okay, next if you just look for the pressure for the solid in liquid, there is really no effect. So for this we have to check for the gas in liquid. Okay, let's proceed. Effect of pressure. So here we will discuss about the, definitely effect of pressure is valid for the gas only, right? So here comes the Henry's law. If you increase the pressure, the solubility of the gas in that particular liquid will increase. Hence if you increase pressure, solubility will increase, means they are directly proportional. So Henry's law direct, it comes in 2-marker question with its mathematical expression. So please make sure while writing the mathematical expression you are mentioning the abbreviation. So here Kh is the Henry's constant and X is the mole fraction of gas. Next, let's proceed. Here you can see application of Henry's law is going to be super duper important for your examination. First application is definitely to increase the solubility of carbon dioxide in the soft drinks. If you increase the pressure, because initially it was kept in a high pressure, whenever you just open the mouth of the particular bottle, then with a high pressure the CO2 will come up, right? So that's the reason with high pressure CO2 will be soluble over there. So next you can see for the scuba divers, so in order to avoid bends, right, in order to avoid bends, scuba diver, they actually dilute their oxygen tank with helium. Next you can see anoxia, to prevent the anoxia actually can well explained by the Henry's law as well, because in the higher altitude as the pressure is decreased, so brain doesn't get enough amount of oxygen, that's why the thinking ability and other things that actually gets reduced, and that particular condition is called anoxia. That can be well explained with the Henry's law. Next here you can see we will discuss about the effect of temperature. Here KH value, it increases with the temperature, and therefore you can say the solubility decreases. So what you can say, if you increase the temperature, your solubility will decrease. Very important point, if you increase the temperature, your solubility will decrease. So here comes one very important thing, like some question can be asked out of it. So if you increase the temperature, one application, let's say if all the aquatic animal, they don't prefer very warm water, right? So they prefer cold water because there comes maximum soluble oxygen. But if the water is literally hot, then their dissolved oxygen amount also will be less, right? So solubility will also decrease in high temperature. That's why aquatic animal, they always prefers to be there in the cold water. Let's proceed with the part 2. Here we are going to discuss about the vapor pressure, ideal, non-ideal solution. Whenever it comes to the vapor pressure, we will discuss about the liquid-liquid solution. We will discuss about the solid-liquid solution. Okay. So whenever vapor pressure means what? Vapor pressure means whenever you can just discuss about a liquid, in that particular liquid, if it is volatile, then if the container is closed, then the surface, from the surface of the liquid to the wall of the container, there exists the vapor of that particular liquid, and there exists an equilibrium condition in between the liquid surface and the vapor condition. Okay, the rate of condensation and the rate of evaporation, they are actually equal. Okay, that's why they exist in equilibrium. So that particular vapor, whatever the pressure it exerts on the wall of the container, that is called vapor pressure. Okay, so definitely if you increase the temperature, rate of evaporation will increase, and as a result of this, your vapor pressure will also increase. Let's proceed. Here with respect to that, it comes Raoult's law. The Raoult's law is basically a special form of Henry's law itself. Okay, this is also saying the same thing, that if you increase the pressure, the solubility of gas will increase. So in this case, definitely you have to take the solution of two volatile liquid. Okay, in Henry's law it was one gas, one liquid. Here we will take two volatile liquid. Okay, so here also pressure is directly proportional to the mole fraction, that is basically the solubility. Here in case of that constant where we use the KH in case of Henry's law, here we will use the constant, that is the vapor pressure of the pure solvent, that is constant. Okay. So here you can see this is the mathematical form. Okay, so now we can have two component A and B. Okay, now for the two component I will get PA equals to P0 of A into XA, P0 of B into XP. Okay, now in accordance to Dalton's law, what it says, the partial pressure of the partial pressure, that is the total pressure over the solution phase, it actually given by the individual component, the sum up of the individual components pressure, right? So definitely we can just add them to get the total pressure. P0 of PB0 of XB plus PA0 of XA. Next you can proceed modified formula. This is the modified formula. You can see from the total pressure, XB can be replaced with 1 minus XA, and further just a little bit modification, a little bit just multiplying and all you do, and then you will get a straight line equation. Same thing, same type of equation you can get if you replace the XA as well, and you will end up with this type of graph. Very important, this is the graph for the ideal solution that follows, that obeys the Raoult's law. I guess it's clear. Let's proceed. Here you can see vapor phase composition. It is also very important. Like vapor phase composition means that is YA and YB, means in the vapor, in that particular vapor, how much, what is the composition of A and B in the vapor. So composition of A will be PA by pressure of A divided by total pressure, and YB, that is a vapor composition, vapor phase composition of B, it will be equals to PB by PT. Let's proceed further for the ideal and non-ideal solution. For a solution that obeys Raoult's law, we call it ideal solution. They don't obey, then we will call it non-ideal. In non-ideal cases, again two segment will come, positive deviation of Raoult's law and a negative deviation of Raoult's law. Proceed further. In non-ideal cases, they forms azeotropes is going to be one of the most important topic. Let's proceed. Here comes the most important difference in between ideal solution and non-ideal solution, very important for your board examination. You can see it is obeys Raoult's law, that doesn't obey Raoult's law. Delta H mix, delta V mix equals to 0, they are not equals to 0, and most importantly the interaction in between AA and BB, they are same in ideal gas, and interaction of non-ideal cases, if you see, AB interaction is different with respect to AA and BB interaction. Let's proceed further. here comes the difference between positive and negative deviation. So here you know actually first is the total pressure should be greater than that of the summation, and total pressure for the positive deviation, and for the negative deviation it should be less. Okay, and most importantly the interaction, if you just talk about, then AB interaction should be weaker than that of the AA and BB interaction, and for the negative deviation AB interaction should be stronger than that of the AA and BB interaction. Examples are very important. Ethanol and acetone, they shows positive deviation because ethanol is having very nice hydrogen bonding, acetone is having dipole moment, right? So individual they are having very nice interaction, AA and BB interaction is very strong, but whenever ethanol and acetone they are mixed, what happens? The hydrogen bonds of ethanol gets disturbed. So AB interaction is weaker. Okay, this is how you can analyze. Okay, I guess it's clear to you. Let's proceed further. Here you can see this is how the graphs of the positive and the negative deviation looks like. Let's proceed. Here comes the azeotropes. The definition is very important. When it's a binary mixture, definitely it's the same composition of liquid and the whenever you will see the same composition in the liquid phase of the solution and in the vapor phase as well, that is called azeotropic mixture. So they boil at the constant temperature, and that's the result, that's the reason they cannot be separated out using the fractional distillation method, and that's very important point. Okay, let's proceed. Here also comes two type of azeotropes, minimum boiling azeotropes and maximum boiling azeotropes. So what is minimum boiling azeotropes? Minimum boiling azeotrope shows positive deviation in Raoult's law. One example is given, you can see ethanol and water. Okay, and maximum boiling azeotropes, they shows negative deviation of Raoult's law, and hence you can just see the example, that is nitric acid and water. I guess it's clear. Let's proceed further. Here you can see the most important, the most vital zone for the solution is basically the colligative property, right? From where the numerical problem also comes in, not only in your board examination, also in the KCET. Okay, so here you can see from the colligative property, what are the properties? Relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, osmosis. Okay, and another one is, you can see, abnormal molar mass. So basically what is colligative property? So basically whenever you are adding non-volatile solute in volatile solvent, what I said, non-volatile solute in volatile solvent, then non-volatile solute particles get accumulated on the surface of the volatile solvent. As a result of this, the way the volatile solvent was evaporating, now the surface is blocked. So the vapor will come, the vapor that was coming initially, it will be lesser. Right, and this was the reason why we observe the colligative properties. Okay, so these the properties, these sets of properties we get when the non-volatile solute is added in a volatile solvent. Okay, so let's proceed. First we will see the relative lowering of the vapor pressure. So definitely it's quite obvious that if the surface area of the volatile solvent is occupied by some non-volatile solute, definitely vapor pressure will be released, I mean decreased. That is the relative lowering of vapor pressure, and this is the formula of it, del P divided by P. Okay, and that is directly equals to the mole fraction of the solute. Derivation part I am not going to the detail. Okay, so now here it is just for the revision, so I am just keeping it simple with the formulas only. That will help you to proceed with the numerical problem. Okay, but in case if it is a very dilute solution, then we are just neglecting the number of moles of the solute in the denominator part. That's it. Next we will proceed with the elevation in the boiling point. So elevation in the boiling point is, the reason is basically same. When the solute is added, the vapor pressure is decreased, right? As a result of this, you can see initially the boiling was done here. This is the boiling point, but later whenever the solution is made, the boiling point is here. So there is an elevation in boiling point. Initially, let's say it was getting boiled at the temperature of, let's say random temperature I am taking 90 degree, but later on I am observing, okay, it is 90.3. Right, so 0.3 increasing, right? So this is elevation in boiling point. So here comes the formula, delta TB equals to KB into M. KB is the boiloscopic constant. Okay, and this is the value. This molality is just explained here, nothing else. Okay, this is the formula. Utilizing that, you can just proceed with the numerical. Very important thing. Proceed. Here comes the osmotic pressure. So osmotic pressure is what? Osmotic pressure whenever it stops the flow of the solvent. So in osmosis, what basically happens, from the higher concentration, from the lower concentration zone to higher concentration zone, the solvent molecule passes through a semi-permeable membrane. What I said, lower concentration zone to higher concentration zone, the solvent molecule passes through a semi-permeable membrane. That's it. That is osmosis. So osmotic pressure is what? Osmotic pressure is something that stops the flow of this solvent, right? That is osmotic pressure. So here pi equals to CRD. This is the formula. C is the concentration term here. Concentration term, if you break N by V, further if you break N, you will get W2 by M2, right? Now rest of the things you know. Let's proceed. Here you can see isotonic solution means whenever two solution, both the side of the semi-permeable membrane, they are of the same concentration, they are isotonic with respect to each other. Reverse osmosis, when the direction of the osmosis is getting reversed just by putting some extra pressure more than that of osmotic pressure. That is your reverse osmosis, and that reverse osmosis we take the help of this while desalination. It's going to be super important for your examination. For the desalination purpose, we use reverse osmosis. Next, we are going to discuss about the abnormal molecular mass. So abnormal molecular mass we get because of the association or dissociation of molecules. Let's say I have taken NaCl. So NaCl, whenever I am mixing it inside water, in the water, then what happens? Na plus Cl minus, they are breaking down, right? I started with single particle. Once I am putting it into the water, then it's getting splitted into Na plus Cl minus. So number of ions. Okay, so this is dissociation, right? Association is what? Let's say I'm adding benzoic acid. Okay, let's say I'm adding benzoic acid. So they will dimerize, or acetic acid, they will dimerize, right? Acetic acid will dimerize because of the hydrogen bonding. Association, molecular mass will increase, right? So that can be corrected utilizing the Van 't Hoff factor. So here you can see these are the formulas of the Van 't Hoff factor, 3 consecutive formulas, but most of the cases we will be using this particular formula for the association and dissociation in terms of alpha. What is alpha? Alpha is degree of dissociation. Okay, for dissociation this is the formula. N is the number of particle after or before dissociation. Okay, so after dissociation you can take. Okay, so N is the number of particle after dissociation, and here before, like after association. Okay, maybe whenever you can see 2 acetic acid is getting, they are dimerized, so N will be 1 by 2. But if you just look for this case, for dissociation, NaCl is getting dissociated, Na plus Cl minus, so N will be 2 here, like that. Okay, so this is all about the solution chapter. I guess it's gonna be really helpful for you. Please keep applying the formula, and make sure that you're watching the Brahmastra series for the further clarification on the basis of question and answer, and I guess your solution chapter concepts and question answer will be ready. Thank you so much. To get more such videos, more such information, tips and tricks, please do follow, like and subscribe our channel. Don't forget to share with your friends. Thank you.